Hello everyone. So today in this video, we are going to look into the DL system of assigning the configuration. This DL system, almost in every course that is mentioned in the Indian universities, you will have this DL system of nomenclature to study in brief. Okay, so this system of assigning the configuration, we now don't use. Okay, basically it is kind of limited to carbohydrates and the alpha amino acids. We use them only in a very empirical sense, that is a kind of a very at a broader sense. On a structural correlation we use the DL nomenclature, DL system of configuration, but otherwise we no more use the system of uh, assigning the configuration to the various stereo centers. And another thing that you must note about the DL configuration is that it is a relative way of assigning the configuration. It is not the absolute way of assigning the configuration, and that is why, that is the main reason why we no more use the DL system of assigning the configuration. Now, why it is called a relative method, I'll let you understand as we progress in this video. Okay, so it all started with the work of Emil Fischer. He was a pioneer scientist who worked in the late 19th century, who worked on various carbohydrates. Okay, and he, during that time, developed this planar representation of the carbohydrates. So basically, in his time, what he was studying was monosaccharides. Okay, so basically, he assigned the Fischer projection to various monosaccharides that was discovered at his time. And as he started to discover new and new monosaccharides, it became essential for him to classify them into groups in order to assign them, or in order to categorize them properly. Okay, so for that he used a kind of stereochemical relationship, which he referred to as small d and small l. Okay, which now we know as the capital D and the capital N. Now here, an important thing that we should try to understand is what is this basis of assigning these D and L configurations. So basically he said that it all depends upon the optical rotation of the parent aldose. What do you mean by that? If your parent aldose is dextrorotatory, okay, then you would say, if you are making a compound from a dextrorotatory aldose, that compound would be assigned a belonging to a D family. So if you are starting with a dextrorotatory, then the compound that you're getting from it would be coming under the D family. Similarly, let me use a shortened. If you start from a levorotatory aldose, the compound that you will be getting would be belonging to the capital L family. So that was the basis of his assigning the various compounds to belonging to a capital D or a capital L family. So when he discovered natural glucose and he assigned the Fischer projection to natural glucose, and he came to know that natural glucose had an optical activity that is dextrorotatory. And therefore, he assigned natural glucose to the D configuration. Similarly, natural mannose was also assigned D family because both these compounds were having a dextrorotatory nature of optical activity. Okay, so that was the pure basis how Fischer used in order to classify compounds as belonging to D or L family. So during that time, as he was discovering new and new monosaccharides, he came to synthesize natural fructose from D-glucose and D-mannose. So therefore, since the parent aldose are D-configured, fructose was assigned to have a D configuration. Now, this is a sugar, a monosaccharide. Okay. And when they measured its optical activity, it was levorotatory in nature. So if it is levorotatory, according to Fischer's definition, it should be the L. Okay, if it is minus, then it should be placed under the L family. Okay, so it was little bit ambiguous when he first found this out. So he said that since the initial definition of if your parent aldose is D, the compound should be D. So since we are getting starting from a D aldose and we are getting this fructose, which is not a aldose but a ketose, so we can write it as D minus minus in order to signify that this is a levorotatory. And when he wrote D-glucose, it is understood that it is dextrorotatory. So if suppose the D-configured compound is levorotatory, this symbol need to be written. Okay, so this is how the nomenclature progressed during the Fischer time, that is in the early or the late 20th century, the late 19th century. So another ambiguous thing happened. What was that? When people synthesize manoic acid from D-arabinose, it's a pentose sugar. Obviously, since we are starting from an aldose that is D configured, your manoic acid should be automatically what? It should be D, right? It should be D configured. But what happened? Later on, people were able to synthesize manoic acid also from L-mannose. Okay, if we are able to synthesize from L-mannose, then the manoic acid should be given the L-manoic acid configuration. So this was a little bit confusing. So at that time, people said that it will depend upon historical order. Since the first synthesis that was reported was D-arabinose to manoic acid, therefore manoic acid, we will keep the configuration of D rather than using L. Now here you have to note that now you know the structure of the monosaccharide. That means the absolute structure of the monosaccharides. Now you know. So you will say it's a very trivial thing why they are so confused, because now we know actually the absolute configuration of every stereocenter in the monosaccharide. But at that time, it wasn't known. So it was a synthetic correlation that they trusted on to assign the DNA configuration. They were more or less very, very correct, and in the correct in their prediction of the planar projection formulas, which was later identified to be correct, though their methodology was quite confusing and wasn't that effective. So this was the basis of the D and L configuration. But as you know, since there was a lot of confusion that was coming because we were choosing the parent aldose optical rotation in order to assign the D and L family or the D and L configuration. So in order to avoid that confusion and the ambiguity that you see in these cases that we see here, Rosanoff, a professor in the New York University, he said that let us use a standard. Okay, let us use a standard, and that standard would be nothing but glyceraldehyde. Glyceraldehyde is nothing but the simplest aldose sugar, which is having one chiral center. Okay, so he suggested that let us use glyceraldehyde as a standard, okay, or a reference compound relative to which we are going to decide whether the compounds that are synthesized will be belonging to D or a L configured family. Okay, so accordingly, he assigned the Fischer projection to the glyceraldehyde. So this is the Fischer projection formula to the glyceraldehyde. Now, he said he arbitrarily suggested. So it's an arbitrary suggestion at that time because the active form of D and L glyceraldehyde was not isolated, because um, we knew glyceraldehyde, we knew that the molecular formula is like this, or the structure, a general structure we know about the glyceraldehyde, but we didn't know, we didn't still separate the D and L form, or the dextro and the levo form of the glyceraldehyde, we still haven't separated. Okay, so it was done only in the 1914, but this proposition of glyceraldehyde as a standard was proposed in 1906, very, very early time. So at that time, he suggested that, okay, since it's having a one chiral center, you expect two stereoisomers, one would be dextro, one would be levorotatory. So he suggested that the dextrorotatory form would be having this particular configuration. He arrived at this configuration on the basis of the Fischer structure for the D-glucose. So D-glucose, when he compared this lower part of the D-glucose with the glyceraldehyde, he found it to be having some kind of a correlation. So he said that since D plus, this is dextrorotatory, so D plus glyceraldehyde is having OH to the right. So he kept that D plus glyceraldehyde will be also having the OH on the right side. So it was an arbitrary suggestion. It was a guesswork that he did, but his guesswork was correct, which we came to know later. Okay, when stereochemical correlation between D-glucose and glyceraldehyde was done. So Fischer's basis was also kind of valid now, because since from D-glucose we were able to not directly synthesize D-glyceraldehyde, but rather indirectly compare that D-glucose is having similar configuration to D-glyceraldehyde. So that's how it was established in 1917. But this structure was proposed by Rosanoff in the 1906. So now what was the basis now of the DNL configuration? Initially, it was on the basis of aldose being having a dextrorotatory or levorotatory. We decide it is D or L. Now, Rosanoff suggested that let's have glyceraldehyde as the standard. So according to now definition of of D and L, he suggested that if you're able to make a compound, from D-glyceraldehyde, or if you're able to synthesize D-glyceraldehyde from this compound, then that compound would be given a D configuration. Similarly, if you start with the L minus glyceraldehyde and you come to synthesize a compound, it would be given L, or indirectly, or inversely, if from a compound you're able to synthesize levorotatory glyceraldehyde, then that would be given a L configuration. So this was the ultimate the ultimate definition of the the definition of the DNL configuration. So this was the ultimate definition, where now you have the basis for DNL configuration is the glyceraldehyde. So on that basis was we assigned the configuration of the various compounds as D or L. Okay, so since this particular way of configuration is actually a kind of you're comparing the compound's configuration with the glyceraldehyde, so it's a relative configuration. Okay, so it is a relative configuration. Now you understood, I hope, what do you mean by relative configuration. So why it is called a relative configuration? Because here you are measuring, or you are assigning the configuration of the compound relative to the configuration of the glyceraldehyde. So if the glyceraldehyde is D, your compound is D. If your glyceraldehyde is L, then your compound is L. So it's a relative configuration, and that's why D and L way of assigning the configuration to the or to a stereoisomer is called as the relative configuration, not a absolute configuration. So all this correlation that you see at that time, that is during the early 20th century, okay, was all based on a synthetic correlation. So what we are seeing here is all synthetic correlation. So here what you see is a synthetic correlation. C is a synthetic correlation. So here this correlation or the relative methods of assigning the D and L was completely or purely on the basis of synthesis. Okay, so it's a relative configuration you understood. Now you understood what is the basis of D and L configuration, and you understood how it was done on the early 20th century. Then in the middle 20th century, that is 1951, the absolute configuration we were able to discover of the various stereoisomers. So it was done by a physicist named Bijwart. He actually used X-ray to find out the absolute configuration of the plus tartaric acid, that is the natural form of tartaric acid, which is dextrorotated. And he came to know the absolute configuration of the dextrorotatory tartaric acid to be this particular configuration. So this particular configuration was already given by Fischer. So Fischer already indirectly or by synthetic correlation was able to give this particular structure for the plus tartaric acid, which was later proved by the absolute configuration that was determined using X-ray crystallography. Okay, it's a very powerful tool which we now use to know the absolute configuration at every stereo center. Okay, so that that structure was correct, that was proposed by Fischer. Now, where do we place this? Whether it belong to a D family or a L family, it's very simple to understand because we do a synthetic correlation. So people were able to synthesize from D-glyceraldehyde the levorotatory tartaric acid. Okay, so when they synthesize D-glyceraldehyde from D-glyceraldehyde a levorotatory tartaric acid, we said that a levorotatory tartaric acid would be a D configured, Okay, so that means if the levorotatory tartaric acid is deconfigured, then obviously that means your dextrorotatory would be L configured. Your dextrorotatory would be L configured. Your levorotatory is deconfigured because we were able to synthesize from D. So this dextrorotatory would be L configured. So we were able to successfully assign the tartaric acid also the D and L configuration based on the relative configuration of the D of the glyceraldehyde. But the ambiguity came into play because when people later on were able to also start from the L plus tartaric acid and were able to arrive at D minus glyceric acid. Now this D minus glyceric acid was also being synthesized from the D-glyceraldehyde. So we know that the levorotatory glyceric acid is deconfigured. But as synthesis advanced, people were able to do better synthesis. They were also able to convert L plus tartaric acid to D-glyceric acid. But according to the definition, if we were able to synthetically correlate, you should be able to say that this dextrorotatory should be a D plus glyceraldehyde. So there was an ambiguity you can see here where we know that initially we said that dextrorotatory form is L form, levorotatory form is D form, but this was all synthetic correlation. So here with synthesis, we are now able to convert a L compound into a D compound. So that means you should be able to also write L plus tartaric acid as D plus tartaric acid. Okay, this L plus tartaric acid, you should be able to write it as D plus tartaric acid. So this is the confusion now. So when people use when synthesis start improving, when people are able to synthesize different types of compound, this D and L form of synthetic correlation didn't work very well. And that is the reason why we are no more using D and L synthetic correlation in order to assign the configuration for the stereoisomers. So now what is left behind of the DNL configuration is just the structural comparison with the glyceraldehyde. So we structurally compare the glyceraldehyde with the other compounds and assign them as having a D or a L configuration. Other than that, we are no more using as a synthetic correlation method to assign the configuration of the stereoisomer. So that we will see in the next video. Thank you very much for your attention.